Welcome back to campus. Welcome to Chem 123 in person. So we're going to continue on now with our material talking about kinetics. So first off, as a quick review, I am streaming things out right now. Let me just double check. I believe I got everything recording. So we are still recorded now in campus, and we have at least some version of this streamed out through the Zoom link. If you are logged in this room to the Zoom link, please, please, please make sure that you mute your sound. Otherwise, it's going to be amazing echo feedback at that point. Again, you shouldn't have to log into Zoom here in class. We're going to try it out. We'll adapt. We'll learn together how we pull this all off. But I cannot tell you how excited I am to be back in front of class. It's been 2 years since I've been inside of a big class, so hi, guys. This is why I started doing this. I'm very happy to see you guys in person. What we're going to talk about today, so who knows what kinetics is? Generally speaking. Yeah, yell it out. What's that? Movement. Okay, that's one part. That's kinesiology, usually, in terms of like, study of movement. What else? You're right, it's got something to do with movement. Change over time. That's exactly it. Chemistry, fundamentally, the reason I got into chemistry is kinetics. Chemistry is boring if you look at it from the perspective of the thermodynamics part of it. That's all you see is where things end up, state functions. That's one part. That's important. Thermodynamics teaches you what's possible. Kinetics teaches you how to get there. Kinetics is about reaction mechanism. Kinetics is about how long something takes to happen. Kinetics is understanding how to actually achieve the goal of change over time. The reason I got into synthesis was because I had an amazing professor. His name was Paul Anastas. He was a synthetic chemist. He was talking about green chemistry. Green chemistry is the idea of replacing the kind of things like toxic petroleum, CO2 in the atmosphere, and basically saying we as synthetic chemists have the power. The statement he made was, as a synthetic chemist, you are the architect of matter. If that doesn't move you, you are dead inside. I'm sorry, there's nothing else I can do. The fact is, you have the ability to understand change in time, and kinetics is how you get there, because this is what teaches what's possible on glacial timescales, days, minutes, picoseconds, and understanding that is critical. So, reaction kinetics is focusing on the path. If you talk about what we just did in terms of like compression, or changes on first law. So again, quick reminder for the midterm up this week. What is the first law? What is the statement of the first law? How could you define that? That is conservation of energy, right? We're saying that the total delta E for two different states is constant, and what we have as currencies of energy is heat and work, two types of currency. Those are our path variables. Kinetics focuses on the path. We may be coming to the same state, but there are a lot of different ways to achieve that. Kinetics looks at how we get there. So it's a focus of changes of concentration from some starting state over time. It's these snapshots, these visualizations of reactions as it is happening. So the thing I want you guys to repeat, change over time. That is fundamentally what we guys are going to be doing. This is a typical representation of change over time. The constant reaction graphs you're going to see is some starting material, A, turning into B, and as that happens, there's a depletion, a loss of concentration of A, and the formation of B. A turns into B. And you notice, what about this? Oh man, I haven't done this in a while, so I'm going to sound like a 14-year-old. Does this look like equilibrium? Why not? What is about the statement of equilibrium that defies what we see here? In terms of the overall picture. Equilibrium talks about what? No net change, right? We are at equilibrium when it is reached a state where there's no more change. Here, we're watching that change in live action. When we're over here, this might be equilibrium, right? When there's no more further change. But the kinetics graph we're looking at is that entire approach to equilibrium. It's how you got there. So once again, it is the path that we're looking at here. Kinetics can be used in a quick snapshot to look at different reactions and rank them and say A to B is slower than C to D. And when we express it like we see here on the top, we've got A going away, B coming in, and the bottom we've got C going away, D coming in. Now what do you see? What are key features that support those conclusions? Why is C to D faster than A to B? Give me something about these graphs that you can see and say, ah, yeah, that's why. Yes? Good point. The intersection here on this lower graph here happens at a sooner time point than this intersection here. What does that intersection represent? In terms of where it is on the process of the reaction, that's what that crossing is special, yeah. Which is also known as what percent conversion, probably? Halfway. You've lost half the starting material, you've produced half the problem, that's 50%. Right? That's that crossing point where you now have more products than starting material, so you've used up an equal amount, if mass balance is perfect. Yeah, so you can say that crossing point happens earlier, and as long as mass balance, like all starting material becomes all product, yeah, that's a really good indication of that's faster than that. Give me one other thing on this graph that you can see, yeah. The slopes of the lines, exactly. If you watch this here, this slope here is a gentle slope. Versus this one here, this is a double diamond, this is bunny hills, right? What you've got is a steeper slope, a steeper slope. Remember, we are graphing concentration against time. So what we're really saying is the change in concentration over the same time interval right here is bigger. D starting material, dt, is a larger number for the same slice of time. All we're saying it's a bigger slope, and that's just looking at 2 points. Yes, those are the two things you can draw on. The slope of the lines are steeper, faster. 50% of the reaction, halfway, happens earlier. Those are two things you can gravitate to. So this is what we start talking about. We have a language to qualify or quantify these things. If this is what we've got, we need a mathematical representation to talk about this, and it depends on the interval we're going to talk about. If I were to look at this and say, okay, overall here, at this time point, these two I have here, would you say the rate of reaction is the same at this first time point as compared to the second time point? Is it the same rate of reaction? Why? How do you make that conclusion? Slope, right? What we can say is, if I look at the tangent of the line right here, so what I'm saying is, what is the change in concentration for some very small time interval near this first point compared to the change in concentration near this second point, again, same small slice of time. So what I'm saying really is the derivative, right, the tangent of that line, the slope of that line at that point tells me about the rate, and it's different. So what we're saying is that for some reactions, and this is just one reaction, this is very typical. We see a lot of reactions that follow this kind of profile. This kind of feels normal if you've ever looked at reaction kinetics. They're not constant off the time. We start fast and it gets slower. Now, why would that be? What are the reasons that that's like, yeah, that makes sense? Why would a reaction get slower as it runs?
There's less reactants.
And what was that kind of a statement of? It's fuel, right? If you use up the fuel, your reaction gets slower. It's like a fire or something else. You're running out of gas, effectively. That's one way. Now, there are some mechanisms where this does not apply, where it just crashes through no matter how much fuel you have. There's some reactions where this slope, or the change in rate, looks very different. This is a gradual one, and there's some that are precipitous, that if you don't have enough material, nothing will happen. So do not look at this as a complete overall. All we know is the rate of reaction may change as the reaction runs. And one of the ways that happens is we're using up something that's driving the reaction, that's making the reaction happen. So we need a way of mathematically expressing this for any reaction. The function of this line right here, we need a mathematical equation that describes how that thing will change. So we define rate as the change in a reagent over time. And the rate can be with respect to either the starting material or the product. We call rate, remember, if something goes away, that's a rate, change over time. If something shows up, change over time. But we need a single value, rate, some number, that equates those two. So if you notice, the rate of reaction is defined as the negative change in starting material, which equals the positive change in product. Now, why would that be? Why do we put a negative sign for reactant, positive for product? Why did we have to relate these two? If you're using up reactants, we give it a negative sign, we're creating products. Remember, they have an inverse relationship to each other. If something is a very quick consumption of starting material, it will also, the corollary, will be a quick production of product. So we have a negative sign associated with our starting material by convention. So the rate of reaction is defined as the negative consumption of starting material, which is equal to the positive consumption or production of product, but the same number, right? It's a balanced equation. What that also means is, if we have different stoichiometric coefficients, we need to balance that out. The general equation says, for any starting material, we're going to have a negative sign, so notice in this equation, A and B are starting materials, the rate of reaction is equal to minus dA dt minus dB dt, but we further have this fraction equal to the stoichiometric coefficient. We normalize it based on how many molecules of A and B were reacting. If this was 2 molecules of A and 2 molecules of B, we'd say the overall rate of A would be minus 1 over 2 dA dt, 1 over 2 dB dt. We have to normalize it by 2 because remember, we're trying to come up with a unit number that describes the rate for all things in the species, right? So if we have lots of one starting material, 15 moles of one thing, reacts with 1 mole of something else, we need this concentration factor that makes both of those rate equations equal to each other. So numerically, here's a specific example. 2 molecules of N2O5, it's an oxide of nitrogen, will break down to make 4 molecules of NO2 and 1 molecule of O2, which means the overall rate of reaction can be given as the minus starting material, 1/2 NO2 dt, and minus 1/4 NO2 dt. Remember, positive signs are associated with products, negative signs are associated with starting materials, and the fraction we have, we divide by the stoichiometric coefficient. The reason why is if you were to look at those curves, this is what you'd see for this reaction. If I was going to monitor this reaction, based on the stoichiometry, you notice we're making 4 molecules of NO2, a blue guy. Its curve is 4 times the magnitude of the other product, O2, here in green. But they have the same overall shape. If we were to take 1/4 of every one of the data points here in blue, we would get the exact same curve we're showing here in green. So that's why we do this fractional manipulation. We're saying that the overall rate of product formation for something that is 4 times is equal to the same rate for something that's only 1 time, provided we normalize it by this 1/4. Same thing with our starting material. We're using up, for every 2 molecules of our red guy we use up, we make 1 molecule of our green, which means the rate of consumption minus, for our N2O5, has to be 1/2 the overall rate of our product in green, the O2 dt, okay? That's how the stoichiometric coefficients work into this. It's just a balancing thing, because again, we try to define it that the rate of reaction is constant. It is a number or a turnover, not respective to the moles of material that we're generating, right? We're trying to normalize everything together. So first, that's our first part. How does that feel? Thumbs, thumbs, thumbs. Good. So this is our equality. This is what we call our reaction rate. Next, we have to say, okay, how the equation that describes how the rate changes as our starting material concentration changes is what's known as the rate law. This is an expression that we can derive for any equation, and it talks about how the rate will change as we use up starting material. Most important for a rate law, it only includes the concentrations of starting material. You only describe, we will only look at cases of reactions where the rate law is talking about the fuel. It doesn't talk about product. And the reason why is we're going to look at each one of these reactions as a single, one-way, irreversible reaction. It's not Le Chatelier. We will look at sort of a complicated equilibrium case, something about microscopic reversibility later, but the principle of a rate law is you say, I am using up fuel, I'm getting to product. It doesn't matter where your product is. That does not define you. It's only your fuel. So you only draw in your rate equation starting materials. It's A and B. There's no C and D here. So that's the first thing. It has these elements which are K times the concentration of our starting materials. We'll come back to the last two things. What is K? And what we showed up here is M and N. Those are two other pieces of the rate equation. But fundamentally, the rate equation is a mathematical expression talking about how the rate changes as you use up fuel, starting material only. So here's the pieces of the rate equation. Every rate equation must have a constant, and it's little k. Little k is not big K. What was big K? What was big K we talked about before? Equilibrium constants. What's your favorite form equilibrium constant coming from the acid-base section? K what? Water. K water. What about else? You have two others. K water, Ka, and Kb. Those are equilibrium constants which talk about what? What is an equilibrium constant teaching you? Concentration of products over concentration of reactants at its equilibrium point, right? What was the other one that was kind of looked like that? Wasn't K, was another letter. It tells you about where you are. Q, your reaction quotient, that's right. Those are distributions of concentrations once you reach your equilibrium position. This is not equilibrium, this is the path. So this tells you how, this is a transmission factor. If you guys have ever looked at things like Beer's law, have you heard of Beer's law before? Yeah? Beer's law says the absorption of some material has a constant which relates to the concentration of the material. It's a constant specific to the reaction. So this K, this rate constant, is like a temperature. It is like a heat capacity. It is fundamental to a reaction. It is unique, but it must always be there. And it is not a rate equation. It's not an equilibrium constant. So they change with different reactions. They change with temperature. This is how we make reactions go faster. If we heat up a reaction, we're not changing concentration, but you guys know if you heat a reaction, generally it'll go faster. The reason why it goes faster is because little k will change with temperature. We'll talk about that when we get to Arrhenius equations. It's not an equilibrium constant. It's talking specifically about sort of this transmission factor, how fast we could move. And it may not have the same units every single time. Now what I mean there, let me go over to iPad. So what we're saying is, rate here is always going to equal to d something, let's say dA dt. And if this was a starting material, let's say we've got A goes to B, we can say that this might be an expression of our rate, right? So once again, we have 1 as our unit here, the stoichiometry, and more importantly, this is negative, this is positive because of where they sit, starting material and product. Those are expressions of rate. Let's say for this equation, the rate law was rate equals K times the concentration of A. Now one thing you notice is rate, the term rate. What units should that always have? Rate is an expression of concentration and time. Yeah, what is it? Moles per second, exactly. You're talking about d concentration dt, concentration over time. That's what it has to have. So rate, no matter what this rate equation is, rate will always have units of moles per time. Could be seconds, could be hours, but it's concentration and time, always. Now what that means is, this, A, has units of moles, right? That is the concentration of that species. So what must the units for KB, dimensional analysis, to give you rate in moles per second? Everybody yells it out. It has to be per second, right? K must be, in this case, 1 over second. That way, concentration times time gives you rate in moles per second. Does anybody know what the order, we haven't talked about it yet, what would I call this rate equation? This is a what order rate equation? Okay, we got a 0. Anybody going to vote for first? Anybody vote for second? It's okay, we're not there, that's the next slide. Point is, there's only one thing, A, that changes the concentration, or the rate, right? The concentration of A is the only thing here. This is what we would call a first order rate equation. So the K value for something with only one concentration value is 1 per second, just over seconds. That way, multiplying it out, we're good. Let's look at a different reaction. A little more complicated. B plus C gives us D plus E. And remember, we could write this out. Rate could be equal to, what's the sign for dB dt? Negative D concentration B dt, which equals, I'm going to say, in respect to D, what would I write? D concentration D. Do I need a positive or negative? Positive. Positive, that's right. What about for C? Negative D C dt. These are all expressions of the rate of this reaction for this reaction. Now notice, they're specific, they're unique, they're bespoke. The rate equation is defined by your balanced chemical equation. Now for this one, hypothetically, let's say the rate equation was rate equals K times the concentration of B times the concentration of C. Once again, rate must be expressed in moles per second, let's say. These are both in moles. What is the units of K for this rate equation? Exactly. I'm going to need it per second, right? I've got a concentration, I got a concentration. Okay, that's good. I still need my time. So K is going to have, definitely has to have 1 over second, but we got an extra concentration we need to cancel out. That's in the numerator, which means this rate equation is going to be, I got you, bro. I'll have a concentration term in the denominator. That way, when we multiply these together, this will cancel one of these, and we return rate as, once again, mole per second. So, the important thing, K, the rate constant, is a polymorph. It will shift, change its units to give you rate as moles per second. And it's defined by how many concentration terms you have over here. What do you think would happen if we add one more concentration term? What happens to this guy? Yeah, we just have to add more down here. That's all that happens, right? All we're doing is junking more concentration terms in the denominator of your rate of your K to sort of even things out. What if I measured rate, and instead of being as per second, what if I was doing per hour? What would the term here be? Yeah, your time has to match. So it will change to shift to return your rate with the proper rate equation, or the proper sort of constants over here. Very good. So that's what I mean by it has different units. Pay attention. Yep. For sure, you could. Like, again, the value of K, for kineticists that do this like really, really seriously, they will use Ks almost the same way people like have stock cars or something. Hey, I just measured a second order rate constant of 1.6 per 7 times blah, blah, blah per hour. Ooh, that's a big number. Okay, yeah, but I measured mine as this many per second. Whoa, okay. My point is, the time unit you choose will generally match what you're trying to convey. It's a super fast reaction, which means it's a big number per second. Or it's a really, really slow reaction, so it's a tiny number per year or something. So it will shift and you can convert it. But in that same way, it's the same conversion you would normally have to do to move from seconds to hours, right? Whatever number it is, you multiply or divide by the dimensions you need to convert between the different times. Yep?
The overall rate stays the same.
Well, the overall rate would still be the same, except it's expressed in terms of a different time unit.
Right.
So instead of showing 4 moles per second, it's now 60 times that per minute, right? Yeah?
The infinite order refers to outputs.
No, that's the fun part now. So this is the number one most confusing thing about rate constants. So we defined, remember, the rate equation is rate. We know how to see that. You can look at a rate equation, or a balanced chemical equation and say, I know I'm talking about loss of A over time, or loss of B over time. The rate equation itself, the back part, K times concentration of A times concentration of B, the one rule is that rate equation should only have starting materials in it, not products. That's for sure. So looking at a balanced chemical equation, we can say, for that balanced chemical equation showed up there, the rate equation will only contain my fuel, A and B, no C and D. The order, the multiplier that goes above the concentration, what we call M and N, those are not A and B up here. They're not the stoichiometric coefficient. This, A here and B here, do not equal M and N. That's why we give them different numbers. Why? Does anybody have a hypothesis why that doesn't equal each other? Just because, yeah. It changes with the reaction going on. Well, yeah, but usually these things, the orders, do not change as the reaction happens. Any other theories? Why might a reaction, if I had A and B giving me C and D, let's say one of those things, let's say this bottom of chemical equation actually was rate equals K times A. And B wasn't even there. But that's the balanced chemical equation. Will the reaction happen without B? Looking at the balanced chemical equation, do you need B? Yeah, you need B. No B, no reaction. The rate equation, oh man, I'm so sorry, guys. The rate equation, if we had a rate equation where the order in B was 0, did not show up, if I change the concentration of B, will that change the rate? What does that mean about B? Is it fuel to make the rate faster? It's necessary, but it's not something that's going to drive the reaction. We'll get into that, the very last part of what we talk about here. That comes down to the specific path. That's what's known as the reaction mechanism. The reason these don't match up, the balanced chemical equation, think of that as a state function. It's saying if you start with A and B and this much, you get C and D in this much. That's just your starting state and your final state. That does not tell you how you get between those two. It may not be one step. It could be a lot of individual little steps. And depending on what those steps are, they may not have anything to do with one of those concentrations. The rate may not change. So we have these two things, the power shown in the rate equation. We call it order with respect to one substrate and overall order in the reaction. And those are numerical values. So the way we would say this here, this rate for this hypothetical equation has M order in A, N order in B, whatever those numbers are. The overall is the sum of the two. If those happen to be first, we'd say first order in A, first order in B, second order overall. Okay? Those are true. But in order to determine the orders, yeah, now that you guys back in person, there's no end of puns. To determine the order in A or B, that totally depends on an experiment that we have to run. We need to determine that part experimentally. It is not something you can just glance at the equation and know. And we'll talk about different ways that that can be done. But let's talk about this. Now, we still don't have the clickety-clicky part going. We're going to do this by vote by clap. I know, right? So for the following rate law, which one of them is a second order reaction? Okay, so I'm asking which of these talks about a second order reaction. So is a second order reaction? Okay, is B a second order reaction? I like the hesitancy. So is C a second order reaction? Is D a second order reaction? Is E a second order reaction? Perfect, yes, absolutely. Why? Quick question, what would you call E? What order would E be? 0. There's no concentration. Goose egg, right? What about A? A is a what kind of order reaction? And what about D? We can add. Yes! Not all of us. So yeah, B and C are both expressions of second order reactions. If we want to talk specifically about B, only B. So once again, which of these now talks about a first order reaction with respect to B? A, E, B, okay, C and D. So, even though D is a third order reaction overall, it is first order with respect to B. These are both expressions or ways we can talk about this language on this. Okay, perfect. So, the order of the reaction, where these powers are, must be determined experimentally. We need to go to the lab and do it. This is what I do. This is my day in, day out. If you go around, come into my lab, and you do the whole thing of like, oh, what do you do? Imagine, scene from 300. What do you do? Oh, I'm an analytical chemist. Oh, okay. What do you do? Oh, I'm a synthetic chemist. Okay. You come into my lab? Hi, lab, what are you? Oh, this is what we do. We solve rate equations, we understand mechanisms, and we do this by merging all these pieces together. This is one of the hardest things you can do as a synthetic chemist because it requires you to master every one of these other side disciplines. This is our profession. I love my lab. Okay, so my point is, the first way we can do this is we have to simplify the system. Just like we talked about with thermodynamics, we cannot just dive in and assume this because the rate changes as the reaction changes, right? And there's a couple of reasons why this could happen. Like we said before, the reaction, as it runs, it gets slower because it runs out of fuel. That's one reason. What's another reason that this might get slower? Well, it cools down. That's one, yeah. That means you're working with really bad equipment. You shouldn't do that. What if C hurt the reaction? What if the product was actually in there and acting like a co-conspirator, slowing the reaction down? That would be known as what we call product inhibition. The other way we'd express that is, as the reaction runs, more C messes things up. It gets more complicated. So the way that we do this, the first way is what we call using initial rates. We say that, look, if this is the overall trajectory of the reaction, this first little time point right after we call go, that first split second when the reaction takes off, is the cleanest. It is the easiest to understand. It does not have a lot of product that's going to interfere with this, and we really, really, really know absolutely what the concentration of starting material is. Why? Because I put it in there. I started the reaction here. This is where I have the most control. I can make that measurement very accurately. So the assumption is I will watch the launch, and from that I will infer what happens all the way through this reaction. This is like watching a cannon and say, well, it was pointed that way, we had this much speed, I can predict where it's going to land. But it's that instant at the very beginning that you focus on. So how we do this? We set up a first experiment. Once the experiment's together, I start it with a known concentration of my A and my B, and I measure the rate. I measure the concentration change over some very small time. I might take a couple of them. But what I get is the tangent of the line at this initial point, just that very earliest event. Okay? So now we have two initial concentrations, A and B, and some rate in the reaction, 0.25. Awesome. Can we determine the order yet? No, there's not enough information yet. What we can do is start a second experiment. I'm going to change the concentration in A. I'm doubling it. I'm not changing the concentration in B. I leave it the same. What happened to the rate? Remember, it's still the slope of the line. It what? Double. Doubling the concentration of A doubles the rate of the reaction. What is the order in A? Okay, we got a 2. What else? So what we mean is the multiplicative factor If I double this, this also doubles. It is a 1-to-1 correlation. It is first. Because if I double this and this also doubles, if I triple it, what would you expect the rate to do? If I triple the concentration, rate should. If I 4 times the concentration, rate should. It's a 1-to-1 relationship between that change. Yes? Who knows? At this point, we cannot determine. All I know is I held this constant. With just these two, I know absolutely A is first order, but I have not had enough information to solve B yet. I'm doing it one at a time. So at this point, I know the order in A is first. I don't know what's going on with B because I didn't change B, so don't talk about that yet. How do I determine that, though? What do I do to follow this up? Change the concentration B and keep A constant. We are not, everybody say this together. Well, I was going to say our names. Actually, no, why not? We're in person. My name is, fill in the blank. My name is, fill in the blank. I was going to say somebody had to say fill in the blank. I am a chemist, not a biologist. And I will not change multiple variables at the same time, hoping I can understand what's happening in the system. I am a biochemist. I know, I walk those paths. You do an experiment where you hold something constant. So in this case, I'm going to hold A constant. I will double B. And if I do that, I'm comparing which two experiments. Do I compare first to third? If I only looked at those two and nothing else, that's a problem. If I change both things and I look at the rate, I don't know what caused it. But checking number 2 versus number 3, apologize. Yeah. Doubling the concentration of B while I hold the concentration of A constant, what happens to the rate? It doubles. So what would you predict? If I double the concentration of B and double the concentration of A, what should happen? 4 times, right? And that's what you see first to last. 0.25 to 1. We cannot tell that instantly out of the gate. That's not a unique solution to this because we have 2 different unknowns. But if we have 2 equations, this set of 3, comparing first to second, I can solve the order in A. Second to third, I can solve the order in B. I can confirm my result by first to third, but not out of the gate. I would need something else in that point. Okay, everybody understand that? So remember, what we're saying is this is an expression, the multiplicative rate or order in each comes down to a prediction. If I change, double the concentration of one thing, then I expect a 1-to-1 correlation for both of these. The reaction is first order in both A and B. So, let's put it to use. Here's a series of expressions, different rates, that we took at different initial concentrations. What is the experimentally determined rate law? So, give me an example. You do not need all the experiments at the same time. Which one do you want to start with? Experiment 1 with which one? Okay, experiment 2. Why? What are you solving if you look at 1 versus 2? What are you checking? Yeah, you're checking the concentration of ammonia because you're holding the concentration of NO2 minus constant. We're holding this concentration constant. We're doubling this concentration. What happened to the rate? Approximately. No calculators. Rate looks like a what? Okay, so what does it sound like? First, second, 0? Sounds first. Okay, let's check. What if I took the first experiment and I check it against, let's say, the third experiment? What am I solving in that case? First versus third? Yeah, I'm 4 times the concentration of ammonia. No change in the concentration of NO2. What happened to the rate? About. Also 4 times. That's a confirmation of first. That is a second or a triplicate analysis. And we can go through that same thing for this whole part. 1, 2, 3, and 4, and any comparison in there is a measurement of order in ammonia. I could choose 1 versus 4. I could choose 3 versus 4. Anything where that is the only component that is changing, and look at its multiplicative value as compared to the rate. Okay? All right, so we now know ammonia's first order. What about, how do I solve that last one? What if I took experiment 5 and I check it against experiment 6? So experiment 5, we're not changing ammonia. Experiment 6, NO2, that's double. What happened to the rate? So what do you think it is? First, second, 0? Also first. So if we go through that, I would predict the experimentally determined rate law is rate equals K times ammonia times NO2. Okay, first order in both components. What is the reaction overall? It is a what reaction overall? Second. It is first order with respect to ammonia. It is first order with respect to NO2. It is 2 overall. Okay, and again, we can go through this entire part. Now that you know this, now that this is the truth, you can now check all these others to see if that's consistent, right? Now you could do something where you actually look at any other pairing and say, does this still hold? How would I solve for K now? Yeah?
Just pick a single experiment and then fill in all of the stuff.
Exactly. We have a rate law. We have an expression right here that says rate is equal to K times the concentration initially of these two. Each of these expressions is some known concentration of those species and an instantaneous rate, how fast it was moving right when we knew that concentration. So as long as I pick anything on here and I sub in the concentration of ammonia, the concentration of NO2, and the rate corresponding to it, I can solve for K. And you could do multiple of these and come up with the same value. Do not take this concentration of ammonia, and then, you know what, I like this concentration of NO2, and you know what, 3 is my favorite number, so I'm going to take that rate. It is not that level of, buffet. It's consistent for each experiment, and each is a unique solution to K, and they should all be the same if everything works. So if you do that, at this temperature, we can solve this, that K is equal to 2.7 times 10 to the minus 4. Look at the units. It is per molar per second. Why is it per molar per second? Why would K have to be per molar per second? It's a second order rate law, right? If we go back to our here, we're saying rate must be concentration over time. We have 2 concentration values. Therefore, K needs to have a per second. It also needs to have that per molar to knock out one of these concentrations. So that's all consistent. This is like going back and looking at entropy and saying, do I have joules per mole per temperature? Enthalpy is going to have kilojoules per mole, right? They're the unit values tell you where you are sort of in the point. Is this a big number, small number? Well, I'll have you know. This is one of those things in calibrating yourself based on different magnitudes of rate constants. This is just like if we said, oh, an explosion has 300 kilojoules. Like, that's cool. Is that a lot? There's a scale that you're going to have to learn as well, too, that based on what these numbers go to. This is actually a pretty fast reaction still. Okay, once again, the amazing clap routine. I have an overall reaction up at the top. Methoxide plus methyl iodide, CH3I, reacts to make this ether and iodide. This is a unidirectional, one-way, known as a substitution reaction. And we know, based on other experiments, the rate law is K times concentration of CH3O minus and CH3I, methoxide and iodomethane. Why is there nothing else in here? Why are none of these guys in the rate equation? They're not fuel, starting materials. So what happens if I double the concentration of CH3I based on that rate law? Okay, A, rate doubles. Okay, B, rate is halved. Why not? If I add more fuel, it doesn't usually go slower, right? There's no change in rate. and it's impossible. So we're doubling the concentration of a starting material. Yeah, thanks. We're doubling the concentration of a starting material. We expect the rate to double because it is first order in that component. Last one. What happens to this if concentration of CH3OCH3 is doubled and the concentration of CH3I is halved? So, the rate doubles, the rate quadruples, the rate is halved, the rate is reduced by a quarter, no change. Okay. Rate is halved. Why? No. This is the last one. Look at your two components. You doubled one, you halved the other. That starts to sound like, oh, it should have just evened out, right? What's the role of CH3OCH3? Starting material or product? Is it fuel? You will not go any faster. That's like, cool. Nice job, bro. Doesn't matter. You're only changing the starting material, so it bends on those ones. All right. So, then this is where we're going to end up today. We know that the reaction will change with time. What we're going to need now, we know that initial rates can change. What we're going to come up next is what's known as the integrated rate laws, predicting where a concentration of reaction will be. Take a look at the baseline slides. Take a little bit of a look at the calculus that is needed for this. It's just a little bit. We'll talk to you guys on Wednesday. Talk to you soon.